Alright, gang, here we go. This is Physics, Unit 4, Part 4. We're talking about torque and simple machines. Pretty fun stuff. Alright, so let's start off talking about torque. Alright, so just for a moment, I want to put you back. Think about your time in geometry, probably. Maybe Algebra 1, and your teacher probably took like magnets on her whiteboard or something like that, stuck them on the whiteboard, and you talked about how you could do things. You could take that object, you could move it around the board, you could rotate it, you could flip it over, so on and so forth. And so remember, like when you moved it around the board, just kept it flat, facing the same direction, that you referred to that as translating your object, right? It was translational motion, right? And so when you think about, whoops, I don't have my pen turned on. So when you think about your object, like if you think about a tire that's moving along the road, right? So here's your tire, okay? And so as it's going, right, it's the wheel is turning, right, this way, and because it's turning, as time goes on, your tire is going from one place to the next, right? It's going from here to here, okay? And so you got your your tire here, and it's going this way to this way, right? And so it's translating from one place to the next, right? It's just moving. Now it's also undergoing rotational motion, right? Because it's spinning. And because of that, your tire moves and it turns into translational motion and life is great. Now we've talked about a lot in physics so far. We've talked about how and why does translational motion occur. And you know now that translational motion, or just movement motion, occurs because of forces. Forces make changes in acceleration, and changes of acceleration mean change in velocity, and change of velocity means something's moving. Okay, so anyway, specifically though, in order to cause a rotational motion, we need a new thing called a torque. Okay, and so a torque is the ability is a measurement of the ability of a force to affect rotation. Okay, so torques and forces go hand in hand. Okay, and the torques are kind of like work, but it's a different beast. Okay, and so torque, all right, this is the symbol for torque. It's like a lowercase l with like a curvy top. So that's the symbol for torque. All right, and so it's the ability of a force to affect rotation. So as we look at our forces, we can think about, well, is that going to affect rotation, and how would I calculate that? All right, so think about a cat going through a door. All right, so this is a cat coming through the little pet door here, and when it comes through, if that cat wanted to push that door open with the least amount of force, okay, that cat would have to push on the door as far away from the hinges as possible. Right, and so here's your axis of rotation, right here, and here's your door. In order to have the easiest time opening the door, the cat would have to push on the very bottom. And you already understand this, right? When you're walking out the door of the classroom or anywhere else, if you want to push really, really lightly, push on the side farthest from the hinges, right? If you want to push really hard, you got to push, then you'd push next to the hinges, right? So we know for sure that our torque is going to be dependent upon the length of the lever arm, all right? It's also going to be dependent on the force, right? So as our force increases, then our doors are going to swing faster, so we're going to have more and more torque. So these are the first two big components of our torque. The final big component of our torque is a little bit more complicated. So think about this situation real quick. A cat is walking through the door. Now, when the cat first starts walking through the door here, you can see that every aspect of this force, every component of this force is going to be going into turning this door. Okay, but as time goes on, the cat's going to keep going straight, right? However, only part of the force of the cat is going to be going into turning the door, right? Some of it's just not going to be used for that at all. Okay, and as you go, less and less of this force is going to be applied to moving this door. Okay, so as the cat walks through the door, okay, then your cat is going to be applying less and less torque to the door. Okay, and so one thing that might help you think about this is that when you're walking through a door normally, especially a door that's like going to close on you as you're walking, like the doors at school that are kind of spring-loaded, the door is going to be trying to push. So a lot of times when you're pushing open the door, you'll push the door, but you'll keep pushing it around, right? You'll follow that door with your arm. And that's just natural to do, right? However, in order to calculate the torque on a motion like that, it takes much more complicated math than what we want to do. So for our class, our forces will only be a force that goes in a straight line. Okay, and so we're only going to be thinking about that force and how it applies. All right, so that's the biggest misconception I've run into is that students are trying to think about this force that's changing direction. Our forces will not change direction. Okay, so this torque, that's why this cat is a good example, because that the cat is pushing on the door and it's just going to keep going straight. All right, so the question here says, which situation above will produce the most torque on the cat flap? Well, the one that produces the most torque would have to be figure A. It would have to be this guy here, and that's because this force is perpendicular, right? So this angle between the force that the cat is applying and the distance to which it's to the axis of rotation is a 90-degree angle. So every aspect of this force will be channeled into moving that door and creating a torque. All right, so here's our formula for torque. Okay, torque, remember lowercase l with the curvy top, is equal to force times distance times sine theta. Now you'll notice this looks a whole heck of a lot like energy, or sorry, work. Okay, now it's not quite work. Okay, the SI unit for force, or for torque, is the Newton meter. Okay, it's not a joule because it's not quite an energy. All right, it's an application of a force. All right, now, so if you're looking at this, this is another way of just kind of picturing what's going on and how we've defined things. So here's a wrench, and we're applying our force against this nut. So our nut is our axis of rotation, and then the force is here. So the D is the distance of our lever arm. Okay, so in this case, it's a wrench, and before was the door, the cat door. Okay, all right, so you got this is your D, so that's the D part. This is the force. Okay, now the tricky part is the sine theta. So you got to really pay attention to this. Now remember that our force, the part of the force that we only care about, is the part of the force that's actually doing the work, right? So that's what the sine theta allows us to calculate. And so the sine theta is going to be this angle right here, and it's taking d times that in order, because we formed a triangle here. See this triangle? And we really care about this side of the triangle, because that's the side of the triangle that allows us to actually do work on the wrench. Okay, so it's the perpendicular distance from the axis to the direction of the force. So our force is headed this direction, so we've kind of drawn a dashed line here, and then it's the perpendicular distance, so it's this 90-degree. See that 90-degree right there? So that's the d sine theta. That's the value we care about. All right. A couple other things you need to pay attention to about torque. Torque is positive. Okay, it's a vector, so that means it has a direction. It's positive if it causes a counterclockwise rotation, and it's negative if it causes a clockwise rotation. So here's how I think about this. You ready? So if you have a circle, right, and it's just kind of sitting here, and you're going to cause a torque. Now, always, if you define your torque as being on this side, okay, so if you're going to apply a positive force to this side, well, the positive force would have to be going straight up. This would be a positive force. And if this thing spins, so say it's got some sort of axis of rotation right here, okay, and you apply a torque that goes straight up, that torque is positive, so that means the axis of rotation, or around this axis of rotation, we're going to have to move that way. So this positive force produces a positive torque. Okay, positive force, positive torque. Okay, and then we can do the same thing the other way. We got our circle, we got our axis of rotation, and then same spot, we're going to apply a negative force. Well, if we apply a negative force, that means our object will be turning clockwise, right? So a negative force creates a negative torque. All right, so that's kind of how I keep track of my positive and negative. I have to think about, all right, what's this going to do if I'm applying a positive force on the right side? What's it going to do if I apply a positive force or a negative force on the right side? All right, so we can kind of look at these pictures and we can say, all right, is this wrench going to be a positive or negative torque? Well, so this is our axis of rotation, right? And we're applying a force going up. Well, if we apply the force going up against that wrench, that means the wrench is going to turn this way, right? And if the wrench turns that way, then to me, that is a counterclockwise motion. Okay, all right, so this is counterclockwise, so that means it has to be a positive torque. Down here, Okay, the force, our door is going to go from here. We're applying, the cat is pushing our door going this way. So the way I look at it, it is a clockwise motion because it's going to go this way. So therefore this is a negative torque. So the cat is applying a negative torque. So then, and then one more definition here, net torque is the sum of all the torques that are being applied. Okay, so you can actually use torque to help you figure out making things balance and stuff like that. And when you do that, you would just simply use the net torque, and you'd have to figure out all the different torques and add them up. Alright, so let's do a couple practice problems here. Suppose the force on a wrench is 65 newtons and the lever arm is 20 degrees, and the angle between the force and the lever arm is 35 degrees, so there's our theta. So calculate torque. This one's really easy. Okay, torque is equal to FD sine theta. Okay, our force we're applying is 65.0 newtons. Okay, and our distance, now be careful here, this is 20 centimeters, but remember we never use centimeters in physics. We use our SI units of meters, so it would be the 0.2 meters. 0.200 doesn't really matter though right now. We know it's got 3 sig figs. And then our sine theta, well, it says that defines it right here that the theta is 35. So we can just throw that 35 right in there and we're golden. Okay? So then we take our calculator, we say 65 times 0.2 times sine of 35. We get 7.46. And our units for torque are Newton meters. Nailed it. 7.46 Newton meters. Now, what force would be required to produce the same torque if the force was perpendicular to the lever arm? So really what we're saying here is we've got the same thing, but now we've got a new force that's going to be perpendicular, right? So we're going to have this. This is our new lever arm, right? So now our angle here, this is now a 90-degree angle, which applies, you know, every single one of these would be 90 degrees. So now they want to know the force. Okay, well, force, if we take the same equation up here and rearrange for force, force would be equal to torque divided by d sine theta. Okay, now the torque is going to be the same because it says the same torque, so that would be the 7.46 Newton meters. All right. Okay, and now the distance, well, it's the same lever arm, so it's still going to be 0.2 meters. All right, and then the sine theta, well, let's think about our angle. So sine, so if it's all these angles here, they're always going to be the same when we're perpendicular, so it's just going to be 90. Okay, well, sine of 90 is 1, so really it just turns into 7.46 divided by 0.2, we get 37.3. And it's Newton force, so our unit is in newtons, 3 sig figs, we're golden. We get the right answer, thank goodness. Yes, we did. All right, now we're going to change gears here a little bit, both literally and figuratively. We're going to talk about simple machines. All right, so simple machines, you probably talked about these in middle school. There are 6 simple machines that you need to know. All right, there's the inclined plane, wheel, and axle. Okay, A-X-E-L. I don't remember how to spell that. Whatever. And then wedge, screw, pulley, wheel and axle, wedge, screw, pulley. Oh man, this is embarrassing. Come on! It's hard to do it. Oh, I'm gonna cheat. I had to do it. Simple machines, wedge, screw, pulley. Oh, lever. Duh. You guys are all screaming at your screens right now, aren't you? Lever. All right. Yeah. Anyway, that was pretty embarrassing. Anyway, so you got your 6 simple machines. Now, the whole idea of a simple machines is that it's all about changing the size and direction of the input force. So you're putting some force on it, right? So if you're using a lever, for example, right, you've got your you've got your bar and you've got a fulcrum, right? And you're putting in some force, right? You're pushing down some force, and then based on that, you can lift some mass up and apply some force that way, right? So by applying force, it's going to move your force, and so it's changed the direction, and sometimes it's changed the size. And so by using different simple machines, we can use that to our advantage to get different things done. All right, now the measurement we used in order to figure out how effective our simple machine is called mechanical advantage. All right, so it's the advantage we gain from using mechanics. All right, that's kind of how I remember it. So MA, all right. And so this is the formula to calculate mechanical advantage. All right, we can use the forces or the distances. So if our F out is greater than our F in, then our mechanical advantage is greater than 1, and if our distance in is greater than our distance out, then our mechanical advantage is greater than 1. So essentially, this is how you calculate force out over force in, distance in over distance out. All right, so make sure you keep those straight. Maybe, work on some flashcards or come up with your own methodology to memorize it. All right, so F out over F in, distance in over distance out. So that's mechanical advantage. All right, simple machines essentially alter the force and the distance moved. So over here, we've got, this is, it kind of looks like nothing. So let's just assume this is a truck, right? So you got a truck here, all right, and then, all right, there's our other wheel. So now we're putting a weight on a truck. Okay, now if you're going to lift this thing up if you had to get this up into the bed of the truck, you can just lift it straight up and just put it on the bed of the truck, and now you could figure out the work required in order to do that, right? That'd be super easy. But if we use an inclined plane, because this ramp is helping redirect the force of gravity, okay, the force that you apply this way, okay, is going to be you're going to be able to have mechanical advantage in moving this weight up the ramp. Okay, now because the distance in, okay, the distance in is greater than the distance out. See how much bigger that D2 is over the D1? Okay, then our mechanical advantage is going to be greater than 1, right? Because distance in is greater than distance out. We can also assume then that the force we're applying follows the same suit, right? The force we have to apply here is much greater than the force we'd have to apply here, right? It's a lot easier to push something up a ramp than it is just to lift it straight off the ground. So our mechanical advantage for this inclined plane is greater than 1. Okay, now where life gets more exciting is when we start to think about friction. Okay, so if our ramp is frictionless, then the work would be exactly the same because the distance traveled would be exactly the same. Remember, work equals force times distance times sine theta, or cosine theta, excuse me. Work equals force times distance times cosine theta. Okay, now if the ramp was frictionless, then that means that the force at times the distance one way would be equal to the force times the distance the other way. So the work would be exactly the same. Physics work, right? Okay, but once we have friction introduced, this work is going to be much bigger because now we have to fight against the force of friction pushing the other way. Okay, so we got force of friction pushing the other way. So that means the work going up the hill is going to be much greater than the work going down the hill, which gets us to our last idea here, which is an idea called efficiency. Efficiency measures work output compared to work input. All right. So if there's no friction, okay, then they would have to be equal to each other, right? Because the force times distance would be equal to the force times distance. However, when we have friction, our efficiency is going to go down. All real-life machines have efficiency of less than 1, okay? So, and you can multiply this ratio by 100 to get a percent. So a lot of times you'll see percentage and be like, oh, that machine's 72% efficient, okay? And so you can find the actual efficiency of it by just dividing by 100. So you see that it was 0.72 would be the value. And so in order to calculate it, all you have to do is have the work out. Okay, that's the force times distance times cosine theta divided by the work in, which would be the same thing. Okay, and so we can use those two values there to calculate the efficiency. All right, so that's it for Chapter 7. Congratulations, you made it to the end. Get ready for the exam. It's coming up. do your practice problems. Let me know if you have any questions, and I'll see you on the flip side.